Hello and welcome you all to my YouTube channel JK Academy India. So in today's video we will discuss about the behavior of transformer on load. In last video we have seen the phasor diagram and the transient effect produced in the transformer at no load. In this video we will discuss the behavior of transformer at load. So as shown in the figure, when a certain load is connected across the secondary, this is the load, current I2 flows through it as shown in the figure. The magnitude of current I2 depends upon the terminal voltage V2 and impedance of the load. The phase angle of this secondary current I2 with respect to V2 depends upon the nature of the load, whether it is resistive, inductive or capacitive. In industry, most of the load connected in the secondary of the transformer is in nature of inductive only. In industries, in special purpose, it may be a capacitor also, capacitor banks also, but mostly the nature of the load is inductive. But in this video, we will discuss all type of loads connected across the secondary of the transformer. The operation of the transformer on load is explained below with the help of number of diagrams. When the transformer is on no load, as we have discussed, I0 from the main supply, the no load current I0 produces MMF N1 I0 which sets up a flux in the core. This is talking about the no load. Now, when the transformer is loaded, current I2 flows in the secondary winding. This secondary current I2 produces an MMF N2I2 which sets up a flux phi2 in the core. As per the Lentz's law, this flux opposes the main flux phi as shown in figure B, this one. So figure A shows the no load condition where I0 flows and it produces a flux phi. When the transformer is loaded as shown in figure B, uh, this E2 EMF or the current I2 creates flux phi 2 which is in opposite direction of flux phi. As phi 2 set up in opposite direction to the main flux, the resultant flux tends to decrease and causes the reduction of self-induced EMF E1 momentarily. Thus, V1 predominate over E1 causing additional primary current I1 dash down from the main supply. The amount of this additional current I1 dash is such that the original condition flux in the core must be restored so that V1 equals to E2. The current I1 is in phase opposition to I2 and is called primary counterbalancing current. This additional current I1 dash sorry produces an MMF N1 I1 dash which sets up flux phi in the same direction as that of phi shown in figure C and cancels the flux phi 2 which was set up by MMF N2 I2. Now N1 I1 dash equals to N2 I2 dash ampere turn balancing. So I1 dash equals to N2 by N1 into I2, or it may be written like KI2, where K is the transformation ratio N2 by N1. Thus the flux is restored to its original value as shown in figure D. This one. Here only flux phi is shown because the flux produced by this I2 current phi 2 was cancelled out by the additional current I1 dash supplied from the primary winding. So the resultant flux will become phi again. Thus the flux restored to its original value. The total primary current I1 is the vector sum of I0 and I dash. So I1 dash. So I1 equals to I0 plus I1 dash. This shows that the flux in the core of a transformer remains the same from no load to full load. This is the reason why iron losses in a transformer remains same from no load to full load. So this is your important statement, because iron loss do not vary with respect to the load. Now we will see the phasor diagram of a loaded transformer. Here we are neglecting voltage drop in the windings, ampere turn balancing. Since the voltage drops in both the winding of transformer are neglected, therefore V1 equals to E1. E1 is the induced EMF in primary winding, and E2 equals to V2, that is the secondary EMF. While drawing the phasor diagram, following important points to be considered. First, for simplicity, we have assumed that K equals to 1, therefore E1 equals to E2. The secondary current I2 is in phase, lags behind and leads the secondary terminal voltage V2 by an angle phi 2 for resistive, inductive and capacitive load respectively. This A figure shows for the unity power factor, this is for lagging, and this is the leading. The counterbalancing I1 dash will be N2 upon N1 into I2. Let the, because I1 dash is equal to KI2, here K is equal to 1, therefore I1 dash equals to I2, and it is 180 degree out of phase I2. You can see here, this is the I1 dash and this is I2. Both are opposite, 180 degree out of phase. Here in this case also, whether the load is capacitive or inductive, or it may be resistive, in case of resistive also. The total primary current I1 is the vector sum of no load primary current I0 and counterbalancing current I1 dash. Therefore I1 equals to I0 I1, this is the vector, so the vector sum will be I0 square plus I1 dash square plus I2 I0 I1 dash cos theta, where the theta is the phase angle between I0 and I1 dash. The power factor of the primary side is cos phi 1, which is less than the load power factor cos phi 2 on the secondary side. Its value is determined by the relation that cos phi 1 equals to 0 cos phi 0 plus I1 dash cos phi 2 upon I1. The phasor diagram of the transformer for resistance, as we have shown in B, A, B, C respectively. Alternatively, the primary current I1 can be determined by resolving the vectors. So, IV equals to I0 cos phi 0 I1 dash plus cos phi 2, where sin phi 0 is equal to sin cos inverse of cos phi 0. This is the value of phi 0. IH equals to I0 sin phi 0 plus I1 dash sin phi 2. Hence I1 will become IV square plus IH square का under root. So thanks for watching. It was about the behavior of transformer at full load or load. Take care and goodbye.